Hello class, this is Ms. Chikoy, and this is working on the free response question number 8. This is a longer one, so it's a 12-pointer, 20 minutes. So let's look at the problem. Obviously, if you look at the setup, this probably hopefully looks similar to a lab we did. So it says, a student in a physics class set up an apparatus to observe rotation in which two discs are mounted along a narrow pipe, length L, such that the discs are separated by a distance 1/2 L. The pipe and discs are then mounted horizontally against another vertical pipe, which is attached to a bearing on a lab table, allowing the system to rotate freely about a vertical axis with a small amount of friction which is independent of rotational speed. That is an important point which you will need to use later. So again, you can't have a highlighter, but you can definitely underline doing it. So small amount of friction, independent of anything else. Alright, and the vertical pipe has these two different circumferences, aka two different radii, where C2 is 3 times larger than C1. C1, C2. In trial 1, the students wrap a string around the narrower section, C1, and then apply a constant force, F, to the string for 10 seconds, causing the system to rotate from rest. After 10 seconds, the students allow the system to rotate freely until it comes to a rest. At the start of the experiment, the students engage a photogate, which is triggered by an extended arm as shown in the diagram above. So just when we had the pendulums, like every time it goes through, it's like tick, 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 it hit. So the photogate is attached to an interface that marks the time that the photogate becomes blocked. The output from this interface is shown below. In the diagram, each dot represents the time the arm passes through the photogate. In this trial, the system came to a rest 42 seconds after the first force was applied. And I feel like there's a small error in this graph that's not really going to affect anything, but I feel like should be another tick because it says 42 seconds, but it really looks like 32 or 34. So there may be some typos in this one. Go figure. But that's really not going to affect your answers in any way. And then in trial 2, the students repeat the same thing except they wrap it around C2. And in trial 3, the students repeat the same procedure again, same force, but they move these things outward, i.e. increasing the inertia. So rank the three trials from highest to lowest in terms of the amount of time elapsed between the force being applied and the system coming to a rest. Explain your ranking. So this is a ranking problem. So you need to think which one is going to come to a rest sooner. And essentially trial 1 is your base, and you want to think about how them happen around it. So in trial 1, we have it rotating or pulling about a really narrow section versus rotating about a larger section. So hopefully you can look up these torque equations, but you have your perpendicular force times your radius. Luckily, since we're pulling straight, it's a perfectly perpendicular force, no angles, nothing. So the radius is important because they're all getting pulled with the same force. Larger radius, larger torque. In this case, the inertia doesn't matter. I mean, it will be moving slower, which will come in later in the questions, but as far as your ranking is concerned, it's just our force times our radius for our torque. More torque over more time gets more inertia, gets more momentum, gets going. So first off, you should probably write your rankings, whatever you ended up picking. So in my case, it's the highest and lowest amount of time elapsed. So the one that took the most time to stop is the one that got going the fastest, which is the one with the largest radii. So it would be trial 2 is greater than trial 1 is equal to trial 3. And as far as your answer is concerned, that's really not worth any points. So if you got the answer, great, cool, but you actually have to explain it, and that's where all your points happen. This first question is by far the most important and what all the other three are based off of. So on a 12-point question, this one is worth 6. So first, and I'll just write it in this way to talk. So first you need to indicate that since our radius is highest here, that means our torque is also the highest here. That's for 1 point. Then you also need to think that for indicating that since there is a greater torque, but it's applied for the same period of time, just like, and I'm going to write this to the side because this isn't really included, but remember, this is angular momentum, is just like regular momentum, but with your English things, or impulse. So our change in momentum or our change in impulse, our impulse or our angular impulse can also be described as F delta T. So the angular version is torque delta T, which means the more time with the more torque, it's going to gain more angular momentum. Let me erase those. And so this is where you can include equations, but you have to explain them. You can't just put out this equation, so I just replace torque with FR, and expect anyone to give you points for it. You have to explain it. Then you have to show that across the board, these all have the same friction. So they all have the same, essentially, negative torque from friction. So they all have the same opposing force. And then indicating that since this one had or needs a larger change in momentum to stop, and that if our torque from our friction is all equal, if this is larger, that means we're going to need more time to make it stop. So that essentially concludes why 2 is going to take the most time. So to just do a quick recap, we get a +1 for saying that larger radius, because torque is force times the radius, gets you a larger torque. And then explaining that since you have a larger torque, I'm not really quite sure why I wrote time there, but if you have a larger torque, you're going to have a larger increase in angular momentum. And then it doesn't have to be here, but somewhere you have to show that since it mentions that the amount of friction is independent of anything else going on, they're all going to have the exact same torque from friction. And since they are all experiencing the same torque, but this one had more momentum, if I had more momentum and I have the same amount of torque slowing me down, it's going to take more time to stop. So all this is the part that proves that 2 is definitely greater than 1. So the other 2 points are proving that 3 is equal to 1. So to start off, you should explain that even though, or you don't really have to explain, but the change in the inertia has 0 change in the amount of torque. And so you could reference both of these equations. So the torque's not going to change. Your overall acceleration, however, will. That is a problem for part C. But since they have the exact same force and the exact same radius, you're going to get the exact same torque. And if they have the exact same torque, they'll have the exact same momentum, because it's for the same amount of time. And if they have the same amount of delta L, it's going to take them the same amount of time to stop, making them equal. So you get 1 point for saying that these things are just completely equal to the torque from I, and that since that's all equal, all of your changes are equal as well. Torque from I, torque from 1. And that would be your 1 and 2 points for that. So total of 6 points on this section. On to part B and C. Alright, so both B and C are similar in that there's actually a lot of different options and ways you could have gotten these points. So I'll go over more. You don't have to hit all of these, but essentially points are given in this. So you have to have one, so each one of these, sorry, because that was a 12-point question, each one of these is 3. So you get 1 point for stating 2 correct differences. And I can't spell, I apologize, but I think you know what I mean. So this is stating 2 differences, and then you get plus 1 point for explaining them correctly. So I'm not going to write a full description of each one. I'm going to explain each one, because it's a lot of writing and I do not have that much room. So one possible difference between trial 2 and trial 1 is that you're going to have more dots. Appear between time equals 0 and time equals 10 seconds. And the correct reasoning for this is more torque, more angular acceleration, right? More angular acceleration, the more times you're going to see that little photo gate get blocked every time it spins. 2, dots are closer together. And this is really similar to part 1. But the dots are closer from t equals 0 to t equals 10 seconds. Same reason. Higher torque, higher acceleration. Higher acceleration means those dots, that's going to hit the photo gate more, and therefore it's going to hit them faster, and if it hits them faster, the dots are going to be closer together. Another possible, and again, you only need 2 of these, but there are about 5 possible. So that's 2. Another one is, again, there are more dots after 10 seconds. And the reason being for this is that if it has higher acceleration, same amount of time, it's going to be going faster. So higher acceleration means higher final angular velocity. Higher final angular velocity, the longer it keeps spinning and the faster and the more often it hits at that time. 4, difference between the closest dots and the farthest dots is greater. So this is a little weirder to think about, and I think harder to understand. But it's basically the idea that on your original trial, we have these, it's speeding up, and then it's slowing down. For trial 2, it's just saying that what they mean by the difference between the closest dots and the farthest dots is that we'll still have that, but then they're going to be ridiculously close, and then they're going to spread out even more. So the difference between this space and the farthest space is there's a greater change than that's even too big. I can't even make it small enough. Whereas these are, their smallest bit is that big. So just the overall relative smallest space taking, which again sounds really dumb when I say it that way. This was not one of the ones I ended up doing when I did this. And last but not least, the dots continue for a longer time, which hopefully if you did part 1 is pretty obvious. So your dots go on longer because it takes more time to stop because of all the aforementioned reasons. More acceleration, higher velocity, and if I have more torque, that means I had more momentum, and if I had more momentum and I have the same amount of friction stopping me, I will go on longer, which means you will have more dots. And again, you did not need all 5, you needed 2. And so right if you didn't state them in the same way, but it has to be the same idea of how it looks different and what that has to do with, or why that's happening, or why you would expect to see that. Alright, and then 3 is a lot like, C is a lot like B, except it's talking about trial 3 versus trial 2, so same idea. You get +1 for the 2 differences, and you get +1 for explaining each. And I will quickly go into what those possibilities were. So on this one, since as you could tell from the first explanation, they didn't think there was as much explanation needed for these, so there's actually only 4 options for this one. So 1, fewer dots. So instead of more dots, we should see fewer dots between t equals 0 and t equals 10. For the exact opposite reasons, or the same reasons, I suppose. Higher inertia means lower acceleration or angular acceleration. If I have lower angular acceleration, it's not going to spin as fast. i.e., you're not going to see your photo gate get hit as many times in that first 10 seconds. 2, dots are further apart. So for the same exact reason they said those dots are closer together, these dots are further apart because, again, the lower the acceleration is because of that increase, the more time it takes to go around each time. Same idea. 3, fewer dots appear after 10 seconds. So there are fewer dots after 10 seconds for pretty much the exact same reason as 1, just backwards. I'll explain what I mean in a second. So fewer dots after 10 seconds. So remember, it's still spinning. It's spinning slower, but it does have all these masses on the end, so it has higher inertia. So that means it wants to keep going longer. But it's still going slower even after you stop pulling on it. So it'll spin for the same amount of time. So time's constant. But since it's essentially heavier, it'll keep going. It's like if you roll a heavy bowling ball, it'll keep going, but it's not getting there very fast. So fewer dots after 10 seconds because it's going to keep going. It's just going to go really slow. For, again, the exact same reason as this. Higher inertia means lower acceleration. Even if that means lower deceleration, it's still going to go slower, fewer dots. And then, like this one, the difference between them is different. So it's basically talking about the difference between the spacing. It's smaller. So I'll draw what I mean, and let me just erase this little thing over here. And do a different color, because why not? So on that previous one, and I'm not going to draw a great picture of it, but it shows it increasing and then it's going pretty fast, and then I let it go and it slowly slowed down until it stopped. For your other one, and this, let's say this is the 10-second mark, so that's when it's going at the absolute fastest. For your third one, that's going to be very differently spaced. So that's maybe our 10-second mark. And then again, it's going to slow down much slower until it stops. Same amount of time. What they mean by spacing is that essentially as we get towards the end, this space is about the same as this space, but these are way closer than your closest one over here. Just because, it never got going as fast because it had a lower acceleration. Alright, sorry this kind of turned kind of long. Hopefully it was informative and you understand better how these things spin and how to grade and how to repeatedly state the obvious. Good luck and good night.